Like ammonia, amines are also basic in nature. Their basic nature is due to the presence of a lone pair of electrons on the nitrogen atom. This lone pair of electrons is donated to the proton of an acid to form a new bond. Amines are weak bases as they combine with water to produce fewer hydroxyl ions per unit volume. For example, an alkanamine combines with water to produce hydroxyl ions, as shown in the equation here. By applying the law of mass action to the equation, the base dissociation constant or basicity constant Kb equal to the product of molar concentrations of RNH3+ and OH- divided by RNH2. You get an idea of the relative basic strength of amines from their Kb or pKb values. The larger the value of Kb or smaller the value of pKb, the stronger is the base. By observing the pKb values listed in the table, we can say that aliphatic amines are stronger bases than ammonia. On the other hand, aromatic amines are weaker bases than ammonia. The Kb or pKb values of amines are affected by factors like the inductive effect of the groups present in amines, the ease of solvation of protonated amines, and steric hindrance. Consider the inductive effect of an alkyl group of an alkyl amine. Since it tends to donate electrons, an alkyl group R pushes electrons towards the nitrogen atom and thus makes the lone pair of electrons more available to the proton of the acid. Moreover, the alkyl ammonium ion formed from the amine is stabilized due to the dispersal of positive charge by the plus inductive effect of alkyl groups. Hence, alkyl amines are stronger bases than ammonia. Thus, the basic nature of aliphatic amines increases with an increase in the number of alkyl groups. Therefore, the basicity order of aliphatic amines in its gaseous phase is tertiary amine is greater than secondary amine is greater than primary amine is greater than ammonia. On the other hand, the basicity order of aliphatic amines in its aqueous phase is ammonia is greater than primary amine, is greater than secondary amine, is greater than tertiary amine. This can be illustrated on the basis of the ease of solvation of cation. The positive charge on the nitrogen atom is also stabilized by the effect of solvation in aqueous phase. The smaller the size of the ion, the greater will be the solvation with water molecules and more stabilized will be the ion. Thus, the order of basicity of amines in its aqueous phase is exactly opposite to the order based on inductive effect. Another important factor that affects the order of basicity is steric hindrance. If the size of the alkyl group is small, like the methyl group, then there is no steric hindrance to hydrogen bonding in its aqueous phase. If the size of the alkyl group is larger than the methyl group, then there is steric hindrance to hydrogen bonding in its aqueous phase. As the size of the alkyl group increases, the steric hindrance to hydrogen bonding increases, and the basicity decreases. Thus, the relatively basic strength of primary, secondary, and tertiary aliphatic amines is due to the combination of inductive effect, solvation, and steric hindrance. Now let us consider the order of basic strengths of aromatic amines. By observation, the pKb values of aromatic amines are quite high. This can be explained on the basis of the resonance stability of aryl amines and aryl ammonium ions by taking the example of aniline or aryl amine. The NH2 group in aniline or aryl amine is directly attached to an aromatic nucleus. As a result, a lone pair of electrons on the nitrogen atom is in conjugation with the aromatic ring, thus making it less available for protonation. On the other hand, the protonated aniline or anilinium ion obtained by accepting a proton can have fewer resonance structures than aniline. You know that greater the number of resonance structures, greater is the stability. Thus, aniline is more stable than the anilinium ion. Hence, the proton acceptability or basic nature of aniline or other aromatic amines would be less than ammonia. In case of substituted aryl amines, electron-donating groups such as methyl, ethyl, and methoxy increase the basic strength, whereas electron-withdrawing groups like NO2, X, SO3H, COOH decrease the basic strength. Here's a problem for you to try. Arrange the given amines in descending order of their basic strengths. Try to work out the answer yourself before checking the solution. The descending order of basic strengths of the amines and ammonia is dimethyl amine is greater than ethyl amine is greater than ammonia. This is explained on the basis of plus L effect of the alkyl groups. More is the number of alkyl groups, more will be the plus I effect. Here's another problem. Arrange the given amines in ascending order of their basic strengths. Try to work out the answer yourself before checking the solution. The ascending order of the basic strengths of these amines and ammonia is: paratoluidine is greater than aniline is greater than p-nitroaniline. Here, NO2 has a minus I effect and is thus less basic than aniline, while methyl group has a plus I effect and is therefore more basic than aniline. Diazonium salts have the general formula Rn2X, where R is an aryl group. The counter ion X- may be a chloride, bromide, or hydrogen sulfate, or a tetrafluoroborate ion. The diazonium group consists of two nitrogen atoms, triply bonded to each other with an overall +1 charge. Aryl diazonium salts are used as intermediates to synthesize a wide variety of organic compounds. To name diazonium salts, add the word diazonium to the name of the parent hydrocarbon. This is followed by the anion name. Consider the compound shown here. There is a diazonium group plus an ethyl group at position 4 on the benzene ring with the chloride anion. The correct name of this compound is para-ethyl benzene diazonium chloride. Can you name this aryl diazonium salt? Notice that there is a fluorine substituent at position 3 of the ring, or the meta position with the hydrogen sulfate anion. This compound is named metafluorobenzene diazonium hydrogen sulfate. Primary alkyl diazonium ions are not very stable. They decompose easily and tend to be explosive when dry. Aryl diazonium salts are stable only for short times at low temperatures. Resonance structures help to stabilize the ion by delocalizing the positive charge around the aromatic ring. To prepare aryl diazonium salts, aniline is reacted with nitrous acid at 273 to 278 Kelvin. The nitrous acid is generated in situ by the reaction of sodium nitrite with hydrochloric acid. The overall scheme is summarized here. Due to the low stability of the diazonium salt, it must be used immediately after preparation. To prepare benzene diazonium chloride in the lab, a solution of aniline is prepared in hydrochloric acid and placed in a beaker of ice. The sodium nitrite solution is also cooled on the ice. The solution of sodium nitrite is then added very slowly to the solution of aniline in hydrochloric acid, keeping the temperature below 5 degrees Celsius at all times. If you use a different acid, you will get a different anion for the salt. Benzene diazonium chloride is a colorless, crystalline solid. It dissolves readily in water It is stable in cold water but reacts with warm water. Benzene diazonium fluoroborate is insoluble in water. It is stable at room temperature. The reactions of aryl diazonium salts can be sorted into two classes. Many reactions of benzene diazonium salts involve the displacement of the diazonium group, as nitrogen is an excellent leaving group. Aryl diazonium ions can also undergo coupling reactions, using the nitrogen atoms of the diazonium group to link to another aromatic ring. We first consider the reactions that involve the displacement of the diazonium group. The first group of reactions that we will discuss are known as the Sandmeyer reactions. In these reactions, the diazonium group is replaced by a chloride, bromide, or cyanide ion in the presence of copper 1 ions. Nitrogen molecules are released as a byproduct of the Sandmeyer reactions. Here is a problem for you to solve. Predict the major organic product of this reaction. The first step of the process converts to aminotoluene into the corresponding aryl diazonium salt. You should recognize the second step of the process as a Sandmeyer reaction. Under these conditions, the diazonium group will be replaced by a nitrile group. In the Gattermann reactions, the diazonium group is replaced by a chlorine or bromine group. To carry out these transformations, the diazonium salt solution is treated with the appropriate halo acid in the presence of copper powder. In general, yields for the Gattermann reactions are lower than for the analogous Sandmeyer reactions. Try to solve this problem on your own before checking the answer. Write equations showing the synthesis of this compound from an appropriate aniline derivative using the Gattermann reaction. With these types of problems, working backwards can be a very effective strategy. We need a bromine atom at position 4 on the aromatic ring. So we can carry out a Gattermann reaction using a diazonium group in the correct location. We can make the diazonium salt from the appropriate aniline derivative. Let's put it all together, working forwards from the aniline derivative that we need. We can convert the aniline derivative into a diazonium salt by treating it with nitrous acid. Subsequently, we can treat the diazonium salt solution with hydrobromic acid in the presence of copper powder to form the desired product. The diazonium group can be replaced by iodine ions if the diazonium salt solution is treated with potassium iodide. This reaction forms iodobenzene as the primary organic product. Try to answer this question on your own before proceeding. Draw the major organic product of this reaction. You should recognize the steps involved. Step 1 produces an aryl diazonium ion. In step 2, treatment with potassium iodide replaces the diazonium ion with iodine. The Shannon reaction is a method for making aryl fluorides. In the first step, a primary aryl diazonium salt is treated with fluoroboric acid to make an aryl diazonium fluoroborate, which precipitates. Next, the dry diazonium fluoroborate is heated until it decomposes, releasing an aryl fluoride. Can you give the structure of the expected product for this reaction? You should recognize this as the Shannon reaction. The amine group will be transformed into diazonium group and ultimately be replaced by fluorine. Reductive deamination of primary aryl amines replaces the amino substituent by hydrogen using a diazonium salt as an intermediate. When the diazonium salt is treated with a mild reducing agent such as hypophosphorus acid, sometimes known as phosphenic acid, the diazonium ion is reduced to an arene. Alternatively, this can be carried out using ethanol. Can you complete this reaction? In the first step, the corresponding diazonium salt is prepared. Next, the diazonium group is replaced with a hydrogen atom. Nitration reactions replace the diazonium group by a nitro group. First, prepare diazonium fluoroborate by reacting the aryl diazonium chloride with fluoroboric acid. When the diazonium fluoroborate is heated with aqueous sodium nitrite in the presence of copper, the diazonium group is replaced by a nitro group. Phenols are readily produced from diazonium salts. These reactions cause the diazonium group to be replaced by a hydroxyl group. To carry out these reactions, acidify an aqueous solution of the diazonium salt by adding sulfuric acid at 100 degrees Celsius and heating it. Azocoupling reactions are electrophilic substitution reactions that take place when a diazonium salt is reacted with a phenol or aniline derivative. In these reactions, the diazonium cation acts as an electrophile, while the electron-rich compounds such as phenols and amines act as nucleophiles. The aromatic rings are joined via the nitrogen atoms. The azo products of the coupling reactions have extended conjugation involving both the aromatic rings. As a result, the products are highly colored. They are often used as dyes. For example, para-hydroxyazobenzene is an orange dye. Para-aminoazobenzene is a yellow dye. As we have seen, diazonium salts are very good intermediates for introducing a variety of functional groups onto an aromatic ring. They allow for substitution patterns that cannot be prepared by direct substitution of benzene or substituted benzenes.